This video will be on section 4.2, Symmetry and Transformation. This is all about graphing. The main topics in the section, we have the three symmetries of graphs. There's a lot more, but the main three are what we're going to talk about. Then there's the main parent graphs of functions. As I mentioned here, you don't need to memorize them, but it is helpful to see some of the names and their shapes along with them because we will be talking about some of them as we go through the class. Then most of the section will be spent on graph transformations. We'll first talk about how it works with formulas, what in words will happen if you do something to a formula, what happens to its graph, and then actually, graphing a transformation. All right, so we'll start with the symmetries of graphs. Usually symmetry, once you see a couple problems, if you're not familiar with it, you probably know the idea of being symmetric, and it'll work that way. So our first symmetry is x-axis symmetry. And we say if the graph is flipped over the x-axis and remains the same, this is just one way to think about it. So it doesn't move at all, then it is symmetric to the x-axis. If it does move, it could even be just very minor, but if it does move at all, then it is not symmetric to the x-axis. And the y-axis is a similar idea. You just do the flipping over the y-axis. If it doesn't move, it is symmetric. If it does move, it is not symmetric. And we'll see examples so you can see what I mean. Now at the origin symmetry, there's a lot of ways to think about this. I prefer, since we talk about x and y-axis symmetry, to just go off those. So it says, really one way to think about it is if a graph is flipped over the x-axis and y-axis and remains the same, it is symmetric to the origin. If it moves, it is not symmetric to the origin. All right, so what's really important here when I say flipped over the x and y-axis, what I'm saying is that when you do both. So if you flip it over just one and it moves, that doesn't matter for this. It's where the result after both moving over both is. So we only care about the result after flipping over both. And I believe we have an example here where you'll see that it does move flipping after one, but then it goes back into its spot, the same spot, flipping over the other. All right, so for the following pictures, what we're going to do is you're just going to select all the symmetries it has. And if it doesn't have any of them, so if they're all false, then none of the above. All right, so the first one is this graph right here. And, once again, if you're familiar with symmetry, you might already know the answer, but I'm just going to run through the list and show you the pictures. So we got x-axis to worry about, we got y-axis symmetry, and we got origin symmetry. All right, so what I'm going to do is show where the result would be for each. All right, so this is the x-axis right here. If we flip this over the x-axis, what happens is this little portion below becomes above. You don't have to be super precise, and then it's going to make this downward U shape. And you don't have to draw it perfect. You don't even have to draw it all. You just need to be able to visualize it. But you just simply ask yourself, did this graph move? Well, the line I drew is not the same exact line. So since the graph moved, it is not symmetric to the x-axis. Kind of another way to think about symmetry as if half is on one side of the x-axis and the other half is on the other, and they're the same way. Right, so the y-axis symmetry, if we flip it over the y-axis, this is the y-axis right here. And if we flip this over, then we have this U shape. It's going to stay U shape, but it's going to be on the right side. I wanted a different color. If we flip it over the y-axis, it's going to look, once again, you don't have to be very precise because you're just trying to sketch it. But if we flip this over the y-axis, it comes over here. And very literally, once again, the picture moved, the graph moved. So it's not symmetric to the y-axis. Now finally, if we flip it over the origin, that means we want to flip it over the x and the y. The reason why I like to do it like this is if you think about taking the picture right here in red, where it's flipped over the x, then flip this over the y. That's how I like to check the origin symmetry. So we flip it over both, but we want to do it with the same picture. So this is flipped over x, and then this one is flipped over y. So this is what the picture would be if we flipped it over the origin. If you see another way to do it more easily for you, that's fine. This is just the way I like to do it. But once again, it moved from the original picture. So it is not symmetric to the origin. Right. So I got a couple more here so you can actually see some symmetries. This is an example of one that has no symmetry. Well, as far as X, Y, or origin, so this one is D and E. All right, so the next one here, check all three again. X-axis, Y-axis, and origin. All right, so what happens if we flip this over the x-axis? Well, this line down here would come exactly here to where the bottom line is, and the bottom line would come exactly to where the top line is. And this doesn't move at all. It's on the same exact spot. So since this one doesn't move, it is symmetric to the x-axis. Right, what about the y-axis? What happens if we, actually before I get there, like I said, one way to kind of see symmetry is if half the picture is on one side and half is on the other of that axis, but kind of in a perfect way. And that's exactly what this is. We have these two lines that are, the halfway point is the x-axis. So it works out perfectly. Right, now if we flip it over the y-axis, we flip it over here, we'll get a V shape that goes backwards. Once again, just kind of visualize it, but this one does move. So it is not symmetric to the y-axis. And finally, the origin. I'm going to do the same thing as before. I'm going to take my picture after I flipped it over the x-axis, which is the same as the original. And then if I flip that over the y-axis, I would get exactly where I flipped over the y-axis before because I'm flipping from the same spot. So once again, it moved, which means it's not symmetric to the origin. And so this one happens to have one symmetry, and it's the x-axis. Right, number three. Number three, the graph definitely looks a little more complicated, but as long as we stick with the same thing that we've been doing, it's no more complicated. So the first thing we want to do is flip it over the x-axis. If it helps, kind of think about doing one part at a time. So this part would come down here below. Then this little section will make an upside down U shape above. Then this little section, when it's flipped over, makes a little U shape below. And then this part below comes above. And since this moved, it's not the same picture. It is not symmetric to the x-axis. And also you can use kind of the half thing. This picture looks a little balanced, but it's not symmetric to the x-axis because what's below is not exactly above it as well. Now the y-axis, if you're like me, this one's a little harder to visualize, but it's not terrible. This part over here, when we flip it over the y-axis, comes over here. Looks like it'd be right where that red line is. Then this little section down here, the U shape, will become a U shape on the right side. Then this little mountain looking part on the right side, when it flips over, it goes to the left side, but it makes a little mountain shape. And then finally, the last little portion here, when flipped over the y-axis, goes to the left side going down. And in fact, it would be right on top of where we flipped over the x-axis. So this one also is not symmetric to the y-axis because it moved. So the last one is this symmetric to the origin? And I kind of spoiled it before, but if we take the picture from being red, the red picture where we flipped it over the x-axis, and then we flip the red picture over the y-axis, so this little part will go over here. This little part flipped over the y-axis will go over here. This little part flipped over the y-axis will go over here. And then this little part flipped over the y-axis will match the last part over here. And it does go back to the same spot. This one did not move. It moved in between, but it didn't move at the end. That's what's important. So it is symmetric to the origin. And only the origin. So origin symmetry is the hardest one for sure. You just got to do both and see what happens. Of course, we didn't have an example here, but y-axis symmetry, if this V was like a V here centered around the y-axis, then that would have y-axis symmetry. It is possible for a graph to have all three. Oddly enough, it's not possible for a graph to have just two symmetries. If it has both x and y, it will have origin automatically. but just go through and check them all because it can have 0, it can have 1, or it could have 3. Now for the parent graphs, what I mean by you don't need to memorize, but you should just look at them. There are a couple problems at the beginning of the homework. They'll ask you to match a function with its graph and a function with its name. These are the 8 it talks about. It's just good to know what the shape of graphs look like, but since you have a calculator, you can always just graph them yourself if you need to look at them. They're really the two important ones. Well, I guess the three important ones that we deal with this class are these three. The linear one, which is graphs of lines, the absolute values, which is the graph of a v-shape, and then the quadratic, which is the graph called a parabola. So we will look at these three more in the class. Right. There are, things that we could talk about with all of them, but these are the three we'll eventually focus on. And especially the absolute value one, since we usually least familiar with this graph. Knowing that it's a V shape is very useful. Right, so finally, the main part of this section is graph transformations. Graph transformations are ways to move the graph of a function around. And what we'll study in this section is how moving a graph affects the formula of the function. So here I have a little chart, rules for transformations of functions. The first pair are horizontal shifts, so moving left and right. And I just like to read off in words what the function is saying. So this first one here says shift left h units. What the formula is saying is we replace x with x plus h. Okay, so when we know what that means from the last few sections because we've been dealing with function notation. The second one, if we want to shift right, it's very similar. We still replace x with something, but it's x minus h. Now, these are often mixed up because when you move left, that's negative, and people want to do minus. So it's the opposite there. Now, vertical shifts are usually the easiest because they work exactly like you would think. If you want to graph your graph to go up k units, what we do is we just add k to the end. You sometimes will have to be careful about this. You got to make sure you add it at the very end, not accidentally with something. And then shifting down is similar, except we subtract at the very end. All right, reflections. If we reflect across a graph, reflections always come with negatives. You just got to remember where you put the negative. So if you want to reflect across the x-axis, the negative sign goes in front of the entire function. And then if you want to reflect across the y-axis, the negative goes only on the x, but all the x's. You might have more than one x. You can also think about this one as replacing x with negative x. Right. The last two are the vertical stretch and compress. These really go together. If you're stretching it, what you do is or compressing it, you multiply the function by the number a, what it's telling you to stretch or compress by. The only difference here is that when you're stretching it, a is bigger than 1, it's getting taller. When you're compressing it, a is smaller than 1. So it's getting shorter. You can kind of think about what this does. Is it multiplies the height. So if you're, let's say you're 6 feet tall, if you want to stretch yourself out, you'll get bigger. So you'd multiply your height, let's say by 2, and you'd become 12 feet tall. A little tall, a little too tall, but that's why it's called stretch. If you get shorter, let's say to 3 feet, then it's like multiplying your height by 1/2. So it's smaller than 1. But these are saying multiply the entire function by a. Right, so what we'll do is we'll look at these problems, look at some problems practicing these formulas, and I'll also show you on the graphing calculator how you can check yourself. Because if you do mix them up with the pluses and the minuses or putting the negative on one side, your calculator will tell you that it's wrong. Right, so it says for each of the following, write an equation for a function that has a graph with the given characteristics. And this is my added part. Check by graphing the original and your answer on a calculator. This is not necessary, but if you're working the homework, you can use a number of graphing calculators that are free to you. But I'll show you on the TI-84. All right, so this first one says we want the shape of y equals x cubed. This is just telling you what to start with. And then whatever comes next is telling you what to do to the formula. We want to shift it left 7 units. All right, so what I like to do, whatever you're told to do with the formula, I just like to write in words. That's my preference, to write in words what I'm going to do and then actually do it. Because this part, it could be anything. We could have y equals the absolute value of x or anything at all. This part is really the important thing. So if we want to shift left 7 units, shifting left or right, I'm going to scroll up here just so you can see, even though you're not going to have this on the test, but it's good when you're starting. Left or right means you replace x with something. And if we're going left, we replace it with x plus that number. If we're going right, we replace it with x minus that number. So what we're going to do here is replace x with x plus 7. Because we are shifting left, so we replace it with a plus. And the answer here, we take our x cubed and we replace x with x plus 7. So you get y equals x plus 7 cubed. Now, once again, to check your answer, the homework will tell you if it's right or wrong, but if you want to see it, take your graphing calculator, hit the y equals button. The original was x cubed. I definitely want to graph the original. And I also want to graph y equals x plus 7 cubed. And now just to make sure you're in the standard window, hit zoom and then go to the standard one. I'm going to type in 6. So this is y equals x cubed. It graphs it really fast, but the y equals x cubed is the blue one. The one we changed is the red one. And you can see we definitely shifted left. It's not moving up or down. And that number that we typed in the 7 is going to be correct, but if you want to count 1, 2, 3, 4, 5, 6, 7, it did shift left 7 units. And so that's a way a calculator can help you, but you don't want to just not try to memorize this chart and then just go into this thinking you can use your calculator, because you might not remember how to change the formula. There's a lot of options here. All right, number 2. We want the shape of y equals x squared. Once again, that's what we're starting with. It doesn't really matter. What's important is what we want to do with it. reflected across the y-axis. So reflections always get negatives. When we reflect across the y-axis, what we do is we replace x with negative x. Or think about putting a negative on x. I like the replacement thing just because that's what we've been thinking about. But I'll just go up here to remind you, reflections get negatives. If we reflect across the y-axis, we replace x with negative x, or negative on all the x's. All right, so when we do that, we get y equals, since x is on the inside of the square root, the negative goes with it on the inside. If the x was on the outside, the negative would be on the outside with that. Now, once again, this might bother you, the negative being on the inside, but that's okay because x can be a negative number and then the negatives cancel. But let's go ahead and graph the two. So we get y equals the square root of x is our original in blue, and then y equals the square root of negative x, the reflected one in red. So blue is our original, red is this one. Are we reflecting over the y-axis? Definitely. This is the y-axis. If we reflect the blue over the y-axis, we go right over here to the red. So that is correct. Right, number three. Number three, we have the shape of y equals the square root of x shrunk vertically by a factor of 1/3. Now, in general, it's very hard to shrink horizontally or stretch horizontally unless if you're dealing with special kinds of functions. So you're always going to see vertically, but that's important that it says vertically. And so I'll scroll back up to just remind you we have vertical, stretching, and compress. You'll notice there's no horizontal stretching or compressing in this chart. But what we do when we stretch vertically or shrink vertically is the easiest one of all, because it doesn't matter which one you're doing. All we do is we multiply the function by 1/3 out front. So I like to do it out front, and you should definitely do it out front. So we got y equals the absolute value of x, and we multiply by 1/3. So we get 1/3 times the absolute value of x. Now, if you want to check your answer, you can definitely do that. A lot of graphs are harder to, not super easy to see shrinking or stretching vertically, so you'll often see the absolute value for those. Now, for the calculator, if you want to find the absolute value, you go to Math, go over to the number in UM category, and then ABS is for absolute value. So this one actually makes the bars, but other calculators will just have ABS and put X inside the parentheses or the bars. All right, so that's the original, and then the one in front, we have 1/3 times the absolute value of x. Now this will put the x in the numerator because there's no parentheses. And if we graph this, so this is the original in blue, this is the new one in red, and when we say shrink vertically by a factor of 1/3, what's happening is it's becoming 1/3 as tall. But it still has that V shape, it's just a very wide V shape. Right. Now, that's the answer. I can guarantee you that it's flattening, but it's in the same shape. It's easier to see when it's actually stretched. So if we do like, this isn't the problem we're asked, but if we do 2 times it, you'll see it gets more steep and there's still that V shape. So that one would be twice as tall. If it was said, stretched vertically by a factor of 2, that would be our answer. All right, so we've got a couple more here. The next two deal with 2 transformations. But as long as you follow the rules, the one thing you got to make sure is you just do them in order. So we got g of x is the shape of f of x equals square root of x. We are shifted up 3 units and right 2 units. Right, so when you have more than one transformation, what you want to do is make sure you do them in order. And just do them in order the way you read it. Right, so what does shifting up 3 units do? Shifting up or down, you add or subtract the number at the end. So what we want to do, shift up 3 units, we add 3 to the end. Now, do it one at a time. Don't do both out in words and then try to do them both together. Do one at a time. So we got the square root of x, and then we add 3 to the very end. And then shifting to the right 2 units means we replace x with x minus 2. Right, and this one you have to be careful on because the x is inside the square root, so when we replace it, the x minus 2 and all goes inside the square root. But the 3, since it's at the very end, does not go inside the square root. Okay, so what we do is we take the answer after we did our first shift, square root of x plus 3, and in this one we replace x with x minus 2. So we get the square root of x minus 2 plus 3. Now this one, the other ones all say y. This one for some reason says g of x. So your answer is going to be g of x equals the square root of x minus 2 plus 3. Now we can go ahead and graph the square root of x compared to this and see that it works. We got the square root of x, and then g of x equals the square root of x minus 2 plus 3. And we're supposed to go up 3 and right 2. So think about this like stopping point here, the beginning point for the square root of x, the original. If we go up 3, we're here, and then right 2, and we are here. We have the same shape, and we shifted the correct amount. Right, now the last one, we have the shape of y equals the cube root of x. That is first reflected across the x-axis, then shifted up. Oops, I didn't make the extreme mark. Then shifted up 3 units. So reflecting across the x-axis, that reflections get negative, and the x-axis we put a negative in front of the whole thing. Okay, so we got our cube root of x, and we put a negative in front of the whole thing. Right, then after that we shift up 3 units, which means we add 3 to the very end, not on the x, just like we did last time. We add 3 to the very end. So we got the negative cube root of x, our previous step, and then we add 3. And that'll be our answer. Y equals, so this one's talking about y equals negative the cube root of x plus 3. Now, this one, when you mix reflections with shifting, if you do them in the wrong order, you will always get them wrong. If you only do shifts, you might be able to do them in the wrong order and get them right. But as a rule of thumb, do them the way you read them. Now we can once again graph to check our answer. Now if you want to do the cube root, hit math. There's a cube root button right here. If you wanted to do a different root, you could go down to 5, where there's an x, and then fill in the 3 on the radical with x. Now for those of you with older calculators, if you use this button, you have to make sure you type in the number first. If you want to do cube root of x, you would do 3 and then hit this. Go to the menu and hit this. And now for our transformation, we have a negative in front. Then we have the cube root of x, and then we have a plus 3 at the end. All right, so the blue one is our original. The red one, well, if we reflect across the x-axis, this little blue section goes up here, and this one goes down here. So it has this shape, it's just lower. And then if we shift it up 3 units, it will go exactly there. Okay. So that definitely works out. All right, so the last thing is actually graphing graph transformations in the homework. The homework will tell you to be careful on how to graph it. And they're all set up like this. So they'll give you a graph of something. This one has 3 line segments like this. And we want to graph g of x equals f of x plus 1. Right. What is this telling us here as far as our transformations? Well, replacing x with x plus 1 is telling us that we want to shift left 1 unit. Right? It could ask you any of our transformations, vertical, horizontal shifts, reflections, the stretching and compressing. But this one is just a random one I picked. We want to shift left 1 unit. So the way you do it is you start from the left, so here we shift the left 1 unit, then plot this one first, then go down here and your next stopping point down here at the bottom, go left 1 here, plot this one second, and then go up to our next stopping point and go left 1 here, and then our ending point here, go left 1 here. And if you plot these points, it'll make the lines as you go. The important thing is that you go in this order. If you mix up the order, then it'll get confused and not give you your full credit. Right, but all the shapes are like these, they call them polygons. And you just what I would recommend is writing down on your notes or in your homework book in words what you're doing, what you want to do, and then actually do it on your graph. So if you wanted to reflect about the y-axis, or sorry, the x-axis, then this would stay here, but this point at -3 would go up to +3, so you would do that second, then down here, and then back up. That is our graph transformations.